All right. I think we should start.
All right. Morning, everyone.
Ethan is going to introduce.
We're gonna get quickly started at 11:45. I think we'll hear the sirens and evacuate the building. So today we are very pleased to have Dr. Prakash Koonath, who has more than 25 years of experience in the area of optics and integrated optics. He received his PhD in electrical engineering from the University of Minnesota in Minneapolis. His areas of contribution include coherent lidars, nonlinear optics, optical spectroscopy, optical fiber communications. He has published more than 50 journal and conference papers, holds several patents in the areas of lidars, spectroscopy, and integrated optics. I have visited their company, SiLC Technologies in Monrovia. Prakash and their CEO, Mehdi, just warmly welcomed us. And they also hired quite a few Cal Poly students recently in the last few years. We have current interns who are also in the room. So please help me welcome Dr. Koonath.
Thank you. Thanks for that introduction, Artan. And thank you for the opportunity to present at your physics colloquium here. I'm not sure if this needs to be turned on for recording or not.
I think George.
I think it's already.
It is turned on. Okay, I'll continue.
He says he already did it.
Oh, he already did it. Okay, great. So the title of my topic is enabling machines to see like humans. What I'm going to cover is what we do at SiLC in advancing the coherent lidar imaging technology. Here's an overview. I'll start with who we are and where we are. A brief introduction to coherent lidar and the technology platform at SiLC that enables coherent lidars. And then I will go into some markets and applications where these lidars can be applied in the short range, mid range, and long range. And I'll explain what is meant by these ranges. Quick snapshot. We are a VC-backed company. We are about 80 plus employees. We are your neighbors in Monrovia. So it's about 20 minutes plus drive from here. We are a leader in the coherent machine vision solutions, and what enables us to be a leader is the integration platform that we have, where we can integrate a lot of functionalities for a lidar on a silicon chip. And we have formed strategic partnerships with various movers in lidar. At this point, I want to reiterate what Erkan mentioned, that we have quite strong ties with the Cal Poly folks between the interns we have and also for your alumni. We have about anywhere from 12 to 16 engineers. So for a company of 80 people, you can imagine Cal Poly brings in a lot of weight to the company. And then we are focused on the title of my talk, what is enabling machines to see like humans? So what does that then mean? What is key to human and animal vision? So if you look at the process of vision, which involves the eye, the optics of the eye, the retina, the brain, all that considered, about 90% of the resources are taken up in order to detect motion. That likely comes from evolution, survival. So that's what enables humans or other animals to do fast actions, the hand-eye coordination that we have when we do things, and some predictive behavior. So in SiLC's lidar, we try to enable similar functionalities. So that would be direct measurement of velocity and motion. We call something called a microdoppler. Like, for example, you see the image of a person walking here. The person has some velocity, and the color coding here is based on the velocity of the person. But you also see that the motion when he's walking, the limbs of the body has certain velocity, also different velocity compared to the motion. So that's microdoppler. The other thing that LiDAR enables is very high depth precision. So if you're able to see an object at 10 meters with sub-micron accuracy, then that adds to your vision capabilities.
I don't think I'm able to judge distances to submicron accuracy at 10 meters with my eyes. So are we actually enabling machines to see better than humans?
Oh, definitely better than humans. Yeah. Yeah. With your vision, with the stereoscopic vision, you probably have at a 10-meter depth precision of few centimeters at the most. But with the coherent lidar technology, we are able to do that. Because it's a coherent lidar, it's immune to multi-user interference. So if there are multiple lidars, that are shooting out lasers, one goes into the other lidar, it doesn't produce any interference. And it's completely immune to background lighting. So we routinely do experiments and measurements out in bright sunlight. And it's also eye safe. So that's very key to a lot of applications. So for example, this particular laser pointer that I'm using is lightly eye safe.
But we don't want to test it.
We don't want to test it, of course, but but this is operating at a visible wavelength for obvious reasons. LiDARs operate at a different wavelength where you cannot see the wavelength, but those wavelength ranges, namely 1.5 micron wavelength, they are considered more eye safe. So I'll start with what's more commonly, what's familiar, radar versus LiDAR. What is it that LiDAR can do that radar is not capable of doing? So on the right side, there are some pictures of state-of-the-art coherent radar imaging that's used for tracking and monitoring. So here's the visual image, and here's what the radar produces. And you see there are some pixelated versions of the objects in the field of view, but what is clearly lacking is the resolution, and that's fundamental physics, right? That is, radars, the wavelength of the electromagnetic radiation is centimeters, maybe millimeters, whereas in optics the wavelengths are nanometers, hundreds of nanometers. So the clear difference is that you can, this is the visible picture, and then you can, if you scan, you can see fine features. That's one of the key advantages that LiDAR brings to the table compared to a radar. If you go side-by-side comparison, LiDAR is not going to replace radar, because radar has certain advantages, such as it can achieve long range and wide field of view, and it also tolerates adverse weather conditions. So those are challenging for a LiDAR. Where LiDAR brings a lot of advantages is high resolution ability, so which means ability to detect very small and also slow hovering objects. A lot of, here I'm showing the picture of detecting a drone. A lot of times drones just sit in there and hover. In that mode, radar finds it very difficult to detect, because quite a few radars work on Doppler signatures. When an object moves, then it produces a change in the frequency. Whereas in the case of LiDAR, they are not challenged by that. Can discriminate against very complex backgrounds. Another thing is with the radar is that it's easy to jam because of the wavelength. RF just spreads out, and then it's easy to jam a radar. Whereas in the case of a LiDAR, line of sight is required to jam a LiDAR, and getting a line of sight is a hard thing. And additionally, because you can use lasers with different wavelengths, you can have multi-spectrum imaging and information of polarization, etc. So I'll start with the simplest LiDAR. Simplest LiDAR is a time of flight LiDAR. What do? You send a strong pulse of light to the target you want to detect, and then you use a detector to look at the received pulse. So then you're sitting there and sending a transmit signal and waiting for it to come back, and then the time between that can be used then to figure out how far away the reflection came from, knowing the speed of light. That's the simplest LiDAR. That is easier to explain. What is done differently in coherent LiDAR? It's also called the frequency-modulated continuous wave LiDAR. It's not a mouthful here, but you will hear these terms being used interchangeably, coherent versus. So what happens in a coherent LiDAR is shown here in a very simple fashion. You have a laser that is spectrally very pure, and then you modulate or change the frequency of that laser in time. So the instantaneous frequency is changing in time as a function of time in a linear fashion, as linear as possible. And when you send that light out, you tap part of that light, and that's called the local oscillator. So you keep that, and the light goes out to the target and then comes back after a certain amount of time. And this local oscillator and the delayed version of the light that came back from the target get mixed in what's called a mixer, optical mixer. So when it mixes, they mix together and then are put into a photodetector. There are two frequencies generated. That's the sum frequency, because the frequency of the local oscillator and the delayed version are different because instantaneous laser frequency is changing with time. So when you mix, you get two frequencies, a sum frequency and a different frequency. Sum frequency is typically extremely high and detector cannot respond. So the difference frequency is what you detect, and we call that the beat signal, beating between the local oscillator and what came back from the target. And the frequency of that beat signal is proportional to how far light traveled to the target and came back. So by detecting the frequency of the signal, we can tell where it came from. So that's how coherent LiDAR ranging works. So range is mapped to a particular frequency. And these frequencies are typically in the megahertz to a few gigahertz rate, which is something that photo detectors and other electronics can easily process, detect. One more thing is if your target is actually moving, then the light that is reflected from it will have an imprint of its motion. That's the Doppler effect. So when you detect the beat frequency, there is information about the motion of the target as well. So you get in a single measurement, you get both the range measurement as well as the velocity of the target. And that's what enables a coherent LiDAR to make instantaneous velocity measurement of the object that it is looking.
What's the wavelength of the laser you typically use, and what determines that? Practical sort of availability, or something that's physical that you pick?
Yeah, so if you look at the LiDAR industry, even whether it's time of flight or coherent, quite a bit of it is at 1.5 microns or 1550. Well, a couple of reasons. One is telecom, all the data, about 20 plus years of development of very good lasers and other optical components in that region. The second thing is so this this that I'm talking about, everything is now integrated on silicon photonics. Silicon is transparent at the 1.5 micron wavelength, somewhere from 1.3 to 1.6 or 7. So that's another reason why that particular wavelength is used. The third reason probably is the eye safety. So these are going to scan our eyes. So it's a sweet spot for wavelength eye safety, that particular wavelength. So if you compare time of flight versus FMCW, the key advantages are direct velocity measurement and immunity to ambient and multi-user. In time of flight, it is very sensitive to the background radiation, light that's there. So they have to put fancy filtering, everything in there, and other things. It's not necessarily eye safe because they do need to send very strong pulses of light. Yeah, in terms, so those are the key things. And then another thing, in terms of the detection methodology, time of flight, everything is, things are done in time domain. In coherent detection, because we are looking for a specific beat frequency, whatever signal that you get, you do a fast Fourier transform. So the advantage there is that your noise is spread across a bunch of frequency bins in the frequency domain, which is what it does is that, so your signal to noise ratio for the signal that you want to detect, the beat signal, increases. And its technical term is coherent gain. So those are the key advantages of FMCW versus the time of flight LiDAR. In terms of velocity, which is a key point for advantage for FMCW, time of flight can also measure velocity. However, what they need to do is that they need to make two measurements. First measurement, okay, the range is at x1, and then the second measurement, the range is x2, and then look at the two measurements, and then how much distance did the object move, divide by the time over which these measurements were made. You can make a velocity measurement. In the case of FMCW, in a single measurement, you are able to get velocity information because of you're looking at frequency shifts and Doppler. So in order to recap, the key benefits of FMCW is a very rapid identification of potential threats, classification using the micro Doppler signatures, because we get instantaneous velocity information. And those are key enablers when coherent LiDAR data is considered part of a perception algorithm. It's immune to multi-user interference, very high precision. So the key challenge, of course, is to need to have more complex optical circuits. You need to have a mixer, you need to have a very good laser, and they need to mix it together, and then also integrate the detector that are used to convert photons to electrons. Some of the picture that I'm showing here is, you see this quite often in some of my slides, but here what I'm showing is a drone. It's a drone that's hovering, and the color, the drone itself has a yellowish color, which is, it's stationary, it's not moving, but it's hovering, so the blades are moving. So this is it's an actual LiDAR measurement of the drone, and what you're seeing is the velocity of the blades that it's spinning. This is one of the very commonly used higher end drones, DJI Matrice or something it's called. Some of you may be familiar with that. It was flying at about 100 meters away or something from our LiDAR. So then how do we address some of the challenges here? And that's where SiLC's integration platform comes in. silicon photonics, integrating all these functionalities on silicon photonics. At the heart of SiLC's platform is the optical waveguide. So what I'm showing here is a waveguide that confines light into the core of the waveguide. There are some key aspects of this technology, this platform, silicon integration platform, that makes it suitable for making lidar chips. So one of them is the lower loss waveguides. So you need to have very smooth sidewalls. So when you send light through it, photons do not scatter out. So that's key. The other thing is, it's one thing to lay out in CAD the waveguide structures that you want, but when you transfer that to a silicon chip, if the fidelity of transferring that CAD layout onto the silicon chip is not good, then you end up having crosstalk between the waveguides and other noise factors. So the technology that we use at SiLC was developed over a period of 30 plus years. Initially, it started with sensing, and then it was developed during the telecom, and then it's back to in the sensing arena now. So they have very low crosstalk and noise. Back reflections. Back reflections come in if you have waveguides with very rough sidewalls and other things. You don't want back reflection because you are actually making a lidar, and the lidar is looking for reflections from the target. So if your system itself has a lot of back reflection, that's going to kill the signal that you actually want to see. So these waveguides have very low back reflection. And then integration. So you integrate the mixer and other things, and also you need an active component like a detector on silicon, because once the photons are mixed, you need to convert them into electrons. So we have germanium detectors integrated on the silicon platform in order to convert from the photon domain to electron, then do further process. So all of this, in addition to the laser, silicon is not an active emitter, but silicon is flip chip bonded onto these wafers. So the entire optical machinery that is needed for the lidar is integrated on a tiny silicon chip. So this shows one of our what we call the vision sensor. This is at the heart of a lot of SiLC's product. It's what you have here is the silicon chip is sitting right here. It has the laser, the detectors, and the mixers, everything integrated here. And around it is some electronic circuit to bias the laser, take the beat signal, and then produce the analog, cleaned up analog signal to be given at this point to a DSP chip, which will do further processing of the signals and do ranging and velocity determination, etc. What you also see here is some optics that light sitting in a silicon chip, and the waveguides are about 3 micron. So if you let light go, from diffraction, it will get a pretty large beam within a few millimeters. So you have other optics to collect that light and collimate into a beam size that you want, which you want to send out to the target. So typically we use collimate lenses to collimate the beam to anywhere from a 2 millimeter beam to 16 or 18 millimeter beams. So that's the optics here. So this is one of the first fully integrated solution for a coherent lidar, one of the most compact on the market too. And the other thing is that because everything is done on silicon, it's very scalable, which in using a mature wafer manufacturing process. And finally, it provides more data. What does data mean? It provides depth or range measurement, of course, provides velocity information, It also provides polarization dependent intensity. So even if you send a particular polarization of light to a target, based on the target, nature of the target, its roughness, etc., what you get back is not the polarization that you send. You send a polarization gets scrambled by the object. So you get information about that as well, which is useful in doing material identification. So here's some pictures of what we have done with the LiDAR. Not sure how familiar people are with the terminology point cloud, but that's what you're seeing here. So how are these points generated? So you have you saw this vision sensor, light comes out, and then you put a scanner in front of this, and then you scan at one point, get the range and velocity, then move to the next point, and then the LiDAR then scans the whole scene in front of you and generates what is called a point cloud. It's because it's a cloud of points that you're generating. So I'll start with the top left here. So here's the person sitting, and we generated a point cloud of that person. The person was getting scanned, and you get the displacement of the torso that's plotted here. You can see it's few millimeters of displacement that you are measuring using the LiDAR, and the LiDAR itself was about 5 meters away. This one, so this is a very short range distance because the object that you're detecting is only about 5 meters. This one is an example of ultra long range. So we can see Mount Wilson observatory towers from our building, and we used our LiDAR to image these towers. So this is an optical, the camera picture, and side by side is the LiDAR image, which is about 11 kilometers away. In the camera picture, you don't have any depth information, but here you have, it's actually color coded based on the depth information. So it's not very clear, and we could measure that the distance between these two towers are about 7 or 10 meters. And that measurement was done from 11 kilometers away. And since, this can be, this is an image that's created a bunch of points. So if you use a tool like a MATLAB or something, you can just turn it around and look at different parts of these objects. This is what we are trying to show is that different wavelengths different objects reflect in a different selectively to specific wavelengths. So here, for example, human skin reflects more at a certain IR wavelength compared to another IR wavelength. So we took pictures of these two folks at two different wavelengths, and you can see the color coding is based on the intensity of light that's coming back. So skin versus clothing have different reflectivity. So you get some material information here, and it can lead to some broad spectrum imaging and innovative system architectures. Finally, here, polarimetry. Like I mentioned, even if you send one polarization, different materials will reflect back different amount of light. We call it TE and TM. TE means roughly a horizontal polarization state, and TM means a vertical polarization state. So metal versus metal, you can see you send most of the light is in one polarization, whereas a material like polyester, you see a lot more spread. So some of these can be used for material classification and enhancing images and improve detection. Yeah.
Does it give 3-dimensional coordinates? Can I use it to like automatically grab the 2D image and convert to 3D model? Is that possible? And it gives also the material.
This is a 3D image already.
3D. When you use your sensor directly picture the thing that you're interested in, they give you the 3D information.
Yeah, because it looks like a 2D image, but actually it has depth information.
3D
Yeah,
coordinates.
it has X, Y, Z coordinates.
So with software, with appropriate software, you can actually turn it around and.
Turn it around and look however you want.
Your sensor.
How much is the sensor? Oh, I think we can talk offline about.
How many do you want to order?
Yeah, exactly. Yeah.
Thank you.
Yeah.
It's not 3D scanner. 3D.
Yeah, sure.
What sort of file was that sent to? Was it like a step file or a 3DF or something, or is it something proprietary? The 3D file.
The 3D file, I mean, it's so you get you know, the system the lidar creates its XYZ. So for every point, so imagine this is my lidar. I scan here, I get XYZ information about that point, and then that point, then that point. So it's a collection of XYZ points. You can use any software, Python, MATLAB.
Plus velocity.
Velocity, actually, that's true.
Just in the direction you're looking, or?
Yeah, because Doppler is in the radial direction. So if you're going perpendicular, there won't be any velocity information.
That's why it's 40 and not 60.
Yeah.
Would the output be something you'd easily be able to upload into like a CAD software, like any extra processing?
I think so, yeah. So you could look at it in any, typically we look at, for R&D purposes, we look at it in something, MATLAB, Python, or some things like that. And then there's something called, forgot, PCD format, .pcd, that's a point cloud format. There are specifically softwares that have been used because then you can quickly go and do dimensioning and things like that.
But so that's fundamentally, they're just tables of data. And if you're interested in this sort of thing, you really do want to learn how to think of it as a table of data, a set of numbers that you can manipulate in Python, MATLAB, any software you want, but you don't want to just be restricted to off the shelf, black box. This can read this type of file. You want to be able to learn how to manipulate the data on the level of like rows and columns in a table. Because fundamentally that's all it is.
Yeah, that's pretty much it is. For every object, you get XYZ data. Then you do what you want to do. So yeah, this is all done in Monrovia. So the life of the silicon chip starts here. We are a fabless company, so it comes from our fabs and then it gets diced and polished in our wafer processing lab. We do a preliminary testing of the chip quality, and then again at the chip level, there are some photonic tests where the silicon chip is tested together with the lasers, and then it becomes a module. So that's the sensor that you saw in a previous slide, somebody holding. Becomes a module here. Once it becomes a module and gone through all these testing, we take it to the LiDAR systems lab, where we do a system, the full LiDAR system characterization. So we have we have a 35-meter run here where we put targets of different reflectivities and look at how good the LiDAR performance is, what is the precision, do a lot of scanning measurements. Then we also do reliability testing on it. So how does the LiDAR perform over various damp heat conditions, temperature conditions, etc. This is all in Monrovia, and some of the folks who from here work in many of these labs.
Have 10 minutes.
Okay, I'll go run through the key markets and applications. Focus on mostly on the industrial robotics and also the perimeter security application. So this is for the warehouse automation and robotics that we recently introduced a commercial product. This was announced at what's called the Automate conference in Detroit 2025, and it won the Innovation Award. So what can it do? It's a very simple conceptually very simple. There is a ionic sensor, and then there's a polygon that scans. And so if you imagine one application is a warehouse where think about a warehouse like an Amazon warehouse where they have stuff going on a conveyor belt, all kinds of shapes and sizes, and then you put this scanner the lidar on top, and then you're scanning perpendicular to the belt motion, and then it creates these type of images here. Precision is about 1 millimeter from, it's a roughly flat precision, 1 to 10 meters. You can see on a conveyor belt, this is a business card that's being imaged. Typical business cards about 1 millimeter thick. You can clearly see that. And you can see the reason why these bottles are shown here is because these are some of the hardest things to image, because there's a plastic coating on top of it, and then light doesn't really reflect back. It gets, because if you put a mirror in front of a lidar, you're not going to get anything back because it's going to go away. You need a scattering optic. So these are not necessarily very scattering optic, but you're able to detect, count how many bottles are there, how many bottles are missing, all kinds of information. So this particular ionic trace can do 10 meters. All the other aspects that I talked about in terms of advantages, polarization, insensitivity to ambient light. It's a very wide field of view device. It scans very fast, 600 lines per second. Show you some more pictures here of these examples of this using. So this is a looking at chips on pieces of wood. You could, the point cloud image, you see the defects. If there are some screws sticking out, you see that. This was a foam material where we poured some liquid. Very hard to see in a visual image or a camera image, but because we can look at the contrast in polarization, and you can clearly see that there is some liquid penetration into it. Again, these bottles, this was from one of our customers that they were imaging, and they were amazed to see how well you can see various aspects of something like this. You think about in industrial automation, this is a tire that is being imaged. You can see the highly defined image of the tread, and all it takes is one rotation, and then you grab a image of it, and then back end your perception software can analyze all these things. So this is actually very recent. Actually, we captured this yesterday. So what some of our engineers did was they take it to a rail cross section, and then the lidar is scanning perpendicular to the motion of a metro rail. So you can see all the compartments or the boat, and here in the details, like this particular, I don't know what it's called, the connection for the electric power, and you can see metro rail written on it from the polarization contrast, intensity contrast. Yeah, and this was done at a distance somewhere. The train is at about 7 meters or so. So we were doing these measurements about 7 meters.
This is one-time scan because the train goes away.
Yeah, train goes away.
But for the tire, it is like rotating, and you have multiple shots at that. Does it enhance the capability of lidar? Like if you have periodic scanning, does it accumulate over time and give you better?
Yeah, you can be like in any signal processing, you can average multiple images and improve your precision. But we do have with one rotation, the precision is good enough.
Okay.
But yeah, you're right, you can do multiple.
Okay. I see.
The example of is it like the train? I know it goes very fast, so does the velocity have an impact on the position?
The velocity of the train,
Mhm.
yeah, it can affect impact the precision whenever the object is going fast.
So that maybe a little slow, so it's probably 4 minutes. I just, because people will get, it'll be a jump.
Yeah, I'll just give you a reminder,
Thing goes up.
look at where your belongings are,
Yeah.
because you need to take those belongings in 4 minutes. Okay,
So I'll conclude with the counter UAS. This is where our ultra long range product. So this particular we call ionic horizon is capable of seeing objects like drones 1 to 10 kilometers. Where it adds value is currently radar is doing detection and tracking, and then other modalities like infrared imaging and visual images come into play for classification, discrimination. LiDAR can potentially help in both areas. In case of detection and tracking, for low flying and hovering objects against clutter, it can see better than a radar. Slow moving objects, and in the classification area, looking at velocity information, polarization information, etc. Because one of the challenges with the radar when you're trying to detect drone is, am I detecting a drone or am I detecting a bird or what is it? So having the polarization information and if you're able to see the velocity of the blades of a drone, which is much faster than the flapping of the wings of a bird, etc., you are able to discriminate. In addition, if you're able to bring in multi-spectrum, that will add as well. So here's an example of our LiDAR mounted together with our partners, other instruments for visual, infrared, and also radar, and then tracking. It's not a very nice. You cannot really see the points here, but what actually this cube is doing is tracking the drone using LiDAR information only. And this image you already saw previously. Our drone can be imaged. Nice. I will move to the next slide. And finally, I'll conclude with this autonomy. This is the market that most people are familiar with. So what are things, for the automotive sector? There's a person behind the car here. It's very hard to see in a visual image, but because the person is moving, from the color coding, you can see, typically people jump out in front of you from behind a car. You can see things like that. This is another person, which happens to be me, walking about 300 meters away. And I was and the radar is capable of detecting the motion of my hand. That's why the green color represents everything that's static, and the other colors represent that's moving.
you can start any time.
So-
I'm just giving you this.
And then small objects. Yeah, that's automotive sector. Well, you can also detect tires. Tires are notoriously difficult to detect because they're very low reflectivity objects. So at 150 meter, detecting a tire is very important. This was a intersection we monitored around 400 meters away. Yeah, so this is the visual image here, and at some point the alarm doesn't go off. You will see a pedestrian coming here and walking.
And that's really cool.
Right.
Okay, everyone,
Let's
gather.
go. Questions will be out in the quad. Yeah. Before we move out, please have a big level of applause. Thank you. Thank you.
You can just go and gather outside and ask questions
Yeah.
out there.
Yeah.
Rest of the building.
It's very uncomfortable.
Okay,
Yeah, you can.
good.
Thank you.
All right, I can help you
Oh, it's not too
fill
bad.
it out. Yeah.
I'm also much.
Oh, no, you're not in the hallway yet. It gets worse. It definitely gets worse. See you later, Becca.